We've talked about traditional flaps, which are a rigid body rotation of the aft portion of the airfoil cord about a hinge point. And now I'd like to show you what you can do with that same methodology, but assuming a different flap shape. So this is a paper that I worked on with a student of mine, Jackson Reed, and also a colleague of mine, James Jew, at Wright-Patterson Air Force Base. And this paper is called Geometric Definition and Ideal Aerodynamic Performance of Parabolic Trailing Edge Flaps. So I'm just going to walk you through some of our findings, and I'm not going to go through the math in a lot of detail. I'm just going to point out a few things. The process is very similar to the traditional flap. And actually, I start off in the introduction. We start off and show the development of the traditional flap, but then we get into the parabolic trailing edge flap here, and walk through the geometric definition of that, and then what we can learn aerodynamically from that. Now, this paper was presented at a conference first, and then published in a journal. I'm allowed to upload a preprint version online, and so I will leave a link with this video so that you can go online and download this paper, the preprint version. And then, of course, if you want the official published version, then you'll probably have to pay for either the conference version or the journal version. Okay, so here's our definition. I'm just going to actually jump to this drawing here. So we've got our traditional camber line here, and so that's a solid line until we get past this hinge point, and then the original camber line is this dashed line here, and we get to the trailing edge here, and we allow a hinge point to be defined, and that hinge point can actually be anywhere in X or Y. So you can even define that hinge point above the airfoil or below the airfoil or somewhere close to the camber line. Usually it's really close to the camber line or the cord line, somewhere in there. And so we've drawn it here, but in general, our math works out that you could actually define that anywhere. And from that point, we're going to draw a straight line from that hinge point to the trailing edge, and we call that the flap neutral line. And then we define a new coordinate system where C here is along that flap neutral line, and eta is perpendicular to that. And now we're going to define a parabolic deflection of that flap neutral line relative to that coordinate system. And so you can see this dotted line right in here. Once we've performed that parabolic deflection of that flap neutral line, then it will come down and form this dotted line here. And the length of that dotted line is the same length as our original flap neutral line. And that's a little bit tricky, but you can work through the math here and see how we do that. So anyway, the length of this guy is the same as the original flap neutral line. And then what we do is we just look at the offset of the original camber line to the flap neutral line, and we apply that same offset from this transformed flap neutral line to the new camber line. So we just bend that camber line so that it keeps the same offset to that flap neutral line as it had before. And then, of course, once you have the camber line, then you just need your equation for thickness of the airfoil, and you walk perpendicular to that camber line above and below to map out the upper and lower surfaces of that airfoil. We define, just a couple notes, we define the deflection of that flap as the rotation here of a straight line. So originally it was the flap neutral line, and if you draw then a line from the hinge point down to the trailing edge and put a straight line through that, this angle here between those two lines is how we define the deflection of that flap. Now it's a little bit tricky or optional, I guess. That's what we chose. That's how we chose to define it. You could also define it as the final deflection at the trailing edge, see, but your deflection is continuously changing from from a zero deflection here at the hinge point out to some finite angle here at the tip. And so we just define the total flap deflection this way as the rotation basically of the trailing edge relative to that hinge point. But you could also define it as the final angle there at the trailing edge. And we looked at that as well, but ended up choosing this as the way to define it. So this is the fundamental equation for a parabola in this eta coordinate system. And we have a couple boundary conditions that eta at 0 has to be 0. Of course, there's no deflection here at the hinge point, and also the derivative at the hinge point is equal to 0. So that allows us to get rid of b and c, these two constants in that equation. And then the final constant a in that equation is related to the amount of deflection that we want. And so we have an expression there. So I'm going to skip over a lot of this math. You can work back through it, and we explain each of the steps, so hopefully it's pretty straightforward to follow. And we'll jump down here to this equation for the final camber line with the parabolic flap. And so basically that final camber line, or the slope of the camber line, is the slope of the original camber line as long as we're in front of the x sub f, which is the location of that flap hinge point. And then this is the change, or this is the slope of the camber line behind that hinge point. So this is basically the parabolic flap here. Then we can use well, let's just show some examples here first. So this is this airfoil here is a 2412, the tail end of a 2412 with we're going to put a hinge point at 0.7. And then we show a traditional flap deflection is just a rigid body rotation of that trailing edge area. And then, of course, the parabolic flap is this contoured geometry there. So both of these have the same flap deflection, the way that we're defining flap deflection. So delta F and delta P are both 15 degrees in this example. And then we have our hinge point at 0.7. And this is what the camber line slope looks like for both of those. For no flap deflection, because it's a 2412, you can get the camber line slope, and it looks something like this. And this is across the whole airfoil from the leading edge to the trailing edge. That's what it looks like with no deflection. Now with a traditional flap, you actually you have a discontinuity here in camber line slope. Right at the hinge point. And so we have that discontinuity there for the traditional flap, but for the parabolic flap, it's continuous. And the camber line slope continues to change or more rapidly changes here in the trailing edge region than does the traditional flap. Is basically just an offset here relative to the original camber line slope. Okay, so this is a plot of what the pressure looks like from a panel code on the two different geometries. And so remember, when we plot pressure, we actually flip the y-axis, and that's just convention so that the upper pressure contours here or lines correspond to usually to the upper surface of the airfoil. That's where we have our low pressures, that are, negative pressures, and then the bottom of this plot is showing the pressure on the lower surface of the airfoil, which is generally our positive pressure area. Okay, so let's look at for no flap, the 2412 looks like this. These are the dashed lines in here. So anyway, pretty benign adverse pressure gradient. Remember, adverse pressure gradient is how quickly we go from a low pressure to a high pressure as we go down the back part of this airfoil. Anyway, so this is the original 2412. Now we're going to look at the traditional flap. And this traditional flap, once we deflect it, you see we get quite a spike here right at 0.7, which is our hinge point. We get a really large spike there in pressure. Now, the problem with that is that on the back side of the spike, we have a very large pressure gradient. That's, again, the derivative or the change in pressure as we move back. You can see a very large pressure gradient, and so this induces flow separation. This is one challenge with traditional flaps, is that you kind of have to be careful about flow separation. I'll just draw a picture here. So as the flow comes over here, sometimes this pressure gradient is too great and the flow will separate there. So that's what we can see, that large pressure gradient right here at the trailing edge, or excuse me, at the hinge point. Well, once we go to the parabolic flap, we still get a bump in that near that hinge point, but the pressure gradient isn't nearly as bad here right at the hinge point. But when we move further back, that's where we get a really harsh pressure gradient, is closer to the trailing edge. And so what we would see there is for the parabolic flap, the flow would be able to hold on longer, but then may still separate here near the trailing edge of the airfoil. Now, these data here was computed using a panel code. And so this is not including viscous effects, and so that's why we get such a sharp pressure gradient. In general, viscosity will smooth this out a little bit, so it won't be quite as drastic as we're showing here. Oh, and one other thing, we're using, I can't remember what the radius is that we used on this hinge here. It might have been 0, and so there was literally a corner here, and so that's another reason that we'd see a large spike there compared to the parabolic flap. And a lot of flaps actually put in some kind of rounded type of hinge here in order to keep the upper surface more continuous, or the slope of the upper and lower surfaces more continuous, and so you don't have such a sharp corner, which would cause a pressure spike like that. Okay, so let's look at the performance, and we can use thin airfoil theory to evaluate the ideal section flap effectiveness of the parabolic flap compared to the traditional flap. Now, we've already worked through, there's another video on the traditional flap, and so you should understand the idea of what this means, the ideal section flap effectiveness, and where that comes from. And so here we work through the same type of thing. We're going to use small angle approximations, or small deflection angle approximations. And so when we do that, then our camber line equation simplifies to this effect here from the parabolic flap, and so it's going to be something here that's directly proportional to our flap deflection. So we can plug that into the alpha L0 equation from thin airfoil theory, and what we get is our original alpha L0 minus some term here after we've gone through this change of variables. Remember, we have to change x to theta. Anyway, once we've done that and plugged it in, then we get some term back here that is due to the flap deflection. In fact, it's directly proportional to the flap deflection. So we can integrate this equation here analytically, and we get, and then take the derivative of alpha L0 with respect to our flap deflection, delta P. This is a parabolic deflection. And that derivative is what is called the section flap effectiveness, or the negative of that derivative is the section flap effectiveness. And so here's a closed form solution that depends on theta f, which is the location of our hinge, our hinge point on the cord. Okay, so that's exactly what we've done with the traditional flap previously. And so here's the equation for the traditional flap. This is the closed form solution here from thin airfoil theory for the ideal flap effectiveness. And again, it depends on the location of the hinge point. Okay, so we can now plot these two closed form solutions. And so on the x-axis here, we've got our flap chord fraction. So this is the fraction of the chord that is a flap. And then on the y-axis, we have the ideal section flap effectiveness. Now, just a reminder, what the ideal section flap effectiveness is, it tells us that for every degree of deflection, how much does that move my zero lift angle of attack? And so one of the easiest ways to think about that is if our whole chord was the flap. So CF over C is equal to 1, so that's the whole thing. And we rotated that by 1 degree, a traditional flap by 1 degree, then our effectiveness is 1. That means that is the same as changing our zero lift angle of attack by 1 degree. So we get a 1-to-1 there if we rotate the entire chord and treat that as our flap. Now, if we're only, most flaps are in this region here from maybe 20 to 30%. And so let's say about 30%, when we deflect that 1 degree, we're going to get about 65 or 70% change in zero lift angle of attack. And so that's what this flap or section flap effectiveness is telling us, okay? Now we've got the closed form solution from the traditional flap, and here we have the closed form solution for the parabolic flap. And on top of that, we've actually put solutions from a vortex panel code for the 2412 and the 8420. And this was to look at how does thickness change it. So of course, thin airfoil theory is assuming an infinitely thin airfoil. So that's what the line represents. And then we're showing vortex panel solutions as we increase thickness from 12% and then to 20%. And then we're also looking at camber. How does camber affect this? Looking at a 24 and an 84 NACA camber definition. So, and you can see that the data basically falls right on top of each other. And so really this ideal section flap effectiveness is not, from a potential flow standpoint, is not affected by camber or thickness. Now, of course, when we put experimental data on here, which we have for the traditional flap, that will fall a bit lower due to viscosity, which we're not accounting for here. So the experimental data is usually a little bit lower than the ideal data here. One other thing that I want to point out is that we found some results by Sanders. I believe these were, I'd have to go back and look to remind myself, but I believe that they were numerical approximations. And so they did some numerical computations, and those are the gray squares and then the gray circles here. And so they found this numerically. They computed the lift as a function of flap deflection, and from their data I was able to back out the ideal section flap effectiveness. But I just want to point out the power of these analytic solutions is that we actually now have a solution, an analytic solution that predicts that to very high accuracy. And so we, using this method, we wouldn't have to actually go in and compute the solutions for each of these points, because we have an equation for that. So that's what makes these analytic approaches so powerful. So let's just look at what this curve means for the parabolic flap. So of course, if CF over C is 0, then we don't get any flap effectiveness because our flap has 0 length. But you can see that immediately as we increase the size of the flap, that per deflection, we are getting more change in our zero lift angle of attack than the traditional flap does. And in fact, if we put the entire, if we made the entire airfoil a parabolic flap and then deflected it 1 degree, we would actually get 1.5 times the change in the zero lift angle of attack. And let's just talk about why that would be. So let's say that this is my traditional airfoil camber line. I'll just say that it's a straight line for now. And then let's say that now I've got a parabolic flap that uses the entire chord line here as the parabolic flap. Well, what we've done is actually two things. Our new, if we froze this new geometry and called that our new airfoil, then we would find that we've we've actually built an airfoil here with some camber and a new angle of attack, basically, once we connect the leading and the trailing edges with the cord line. So basically what we've done is we've cambered the airfoil with a parabolic shape, and we've changed the angle of attack. And so those are two things working for us. And so basically that's why we can get a larger than one change in our section flap effectiveness. Okay, so one last thing maybe to point out is that this crosses one at about a flap chord fraction of 0.4. And so rather than building a traditional flap that rotates the entire, if we need more flap authority, sometimes we will rotate the entire airfoil and give it a CF over C of 1. But in our case, if we use a parabolic flap, then we can get that same effectiveness by only rotating 40% of the airfoil, or excuse me, 40% of the airfoil. The aft 40% will give us a section flap effectiveness of 1. Okay, there's other things that we look at here. Let's look at the pitching moment about the quarter cord. Now remember that the quarter cord is the location of the aerodynamic center as predicted by thin airfoil theory. And so we can get that, again, from thin airfoil theory by plugging in this camber line into this equation here for the pitching moment about the quarter cord. And so what we find is that it's going to be the original, and then we have this additional term here due to the flap, and it's directly proportional to the flap again, once we've made the small flap deflection approximations. So we can integrate this second term here and get a change in pitching moment about the quarter cord with respect to flap deflection, because it's proportional here. It ends up just being this term here. We can integrate that analytically and get the change in our pitching moment about the quarter cord with respect to flap deflection, and this is what we get here. That's the equation. And again, from thin airfoil theory, we can look at a traditional flap. Remember the little f here means a traditional flap, and the p up here, the delta p, means a parabolic flap. And so this is the same solution we get from thin airfoil theory for the traditional flap. So let's look at what these look like. This is the pitching moment about the quarter cord with respect to flap deflection. So there's the change in pitching moment at the quarter cord with respect to flap deflection. And remember, the quarter cord is the aerodynamic center of the thin airfoil. Okay, so the traditional equation here, or the traditional flap deflection, is this dotted line. And so we can see, again, I think it's helpful to kind of think through what this means. So if we have a CF over C, again on the x-axis, if we don't have any length on that flap, then of course we don't get a change in pitching moment with respect to, or with a change in deflection. And then if we go to the other extreme, if we say that the entire flap is, the entire cord is the flap, then when we change the deflection, that's the same as changing the angle of attack. And the definition of the pitching moment about the aerodynamic center is that it does not change with angle of attack. And so if our entire airfoil is the flap, then again we have zero change in pitching moment, because it's the same as rotating that entire airfoil, and the pitching moment doesn't change about the aerodynamic center of that airfoil as we change the angle of attack. So that's why it goes back to 0 here. But you can see that in the interim, it creates a negative pitching moment, and that was easy to see actually from those pressure distributions. If we look at the pressure, so this is of the deflected flap. So this is the pressure on the upper surface, and relative to the original pressure on the upper surface, which might have looked something like this, we see that we get a really low pressure region back here, which is going to create a negative pitching moment. And so that's why these numbers are negative here. Okay, so now let's look at the parabolic flap. We see that for the parabolic flap, we actually even get more negative pitching moment per degree of deflection than we did for the traditional flap. And we see that it doesn't go back to 0. We still have some negative pitching moment if we use our entire flap for that deflection. And again, that's because we're adding camber to that entire flap because we're using a parabolic flap. So let's look at, so that pressure distribution looked something more like this, where that low pressure region was shifted even further back than the traditional flap. So this would be the parabolic, and then this would be the traditional flap. And so the parabolic flap had a lower pressure further aft than the traditional flap did, and so that's why we're getting a lower pressure or a lower pitching moment here, more negative pitching moment. And again, we have data from this same group here, Sanders and his co-authors, and you see that it falls right in line with these estimates here. Now, again, we have solutions from the vortex panel method, and you can see they deviate somewhat from these solutions here. So that's just telling us that thickness and camber actually do matter. And so anyway, the thin airfoil theory is not going to be quite as accurate. We need to pay attention to thickness and camber, and of course we're still neglecting viscosity, and so that could change the solution again and possibly move it back closer to the thin airfoil theory. We'd have to look at that in more detail. Okay, we're going to come back and talk about this equation 60 in just a second here. Let's keep going down. Another thing we looked at is equivalent lift deflection. So what if we want to deflect the parabolic flap so that it gives the same lift coefficient as the traditional flap? So this is, we define a ratio here. This deflection ratio is the parabolic flap divided by the deflection of the traditional flap that gives the same lift coefficient at the same flap chord fraction and same angle of attack. Okay, so so this is an example solution here. We've got our hinge point here, and again, this is the 2412 airfoil. We've got a CF over C of 0.3, so that means that our hinge point is at 0.7. And what we solved for here was the flap deflection, the parabolic flap deflection that gave us the same lift coefficient at the same angle of attack as a traditional flap deflection. And so what we found was if we deflected the traditional flap 15 degrees, the parabolic flap only needed to deflect 11.23 degrees in order to produce the same amount of lift. And so actually from thin airfoil theory, we can estimate what that deflection ratio looks like. And this is a plot of that solution. So so here we've got CF over C again on the x-axis, and this is the deflection ratio, how much parabolic flap we need compared to how much compared to the traditional flap. And it's just that ratio. And so you can see over most of the region here, if we look at this equation 59, this is our analytic solution from thin airfoil theory, you can see that it ranges from about 67% up to about 75% flap deflection depending on CF over C. So that means that we're usually between about 70 to 75% flap deflection of the traditional flap. So that's a 25 to 30% less deflection than the traditional flap. And we also looked at vortex panel solutions for small deflections using the vortex panel method. We looked at thickness, so a NACA 0020 and then a 4401 and 4420. So we're also looking at camber solutions or changing camber, and you can see that data all falls pretty close to very near that line there that we get from this analytic solution. However, one of the assumptions that we built into this and also built into these solutions here was that we had small deflections. And when we go to larger deflections, it turns out that these results deviate from this thin airfoil theory solution, because in the thin airfoil theory solution, we built in the small deflection assumption. So as we increase, if we take the NACA 0001, so very thin airfoil, but increase the deflection, then we see that, for example, the traditional flap, if we set that to 30 degrees, then we're ranging more from 80 to 70% here of the in order to get the same lift. That'd be the required deflection from the parabolic flap. So this ratio basically increases with increasing flap deflections, but for small deflections, this thin airfoil theory solution is rather accurate. Okay, so I guess the big takeaway here is that in general, the parabolic flap needs less deflection than the traditional flap in order to create the same aerodynamic response. We're generally deflecting that flap in order to increase the lift on that airfoil or the wing, and or to decrease it, if we deflect it up, I guess. But we get more, we don't have to deflect the parabolic flaps as far as we do traditional flaps, because they are more efficient. They have a higher flap effectiveness. Okay, so then this is coming back to that equation I pointed out earlier that I'll go back up and show you in this plot, but we can look at the pitching moment. So let's say that we deflect the parabolic flap only enough to give us the same lift as the traditional flap does. And so this is the change in pitching moment of the relative to the parabolic flap at the same lift, CF over C, and angle of attack as the traditional flap. So let's go back up and look at that. That's equation 60 that was included in this plot up here of the pitching moment. So remember, we are getting a much lower or more negative pitching moment for the parabolic flap per degree of deflection. Remember, this is per degree deflection for the parabolic flap than we were for the traditional. Well, if we only require the parabolic flap to deflect as much or sufficiently to give us the same delta in lift as the traditional flap, then it creates a much lower or more benign pitching moment than it would if you're looking at per degree. So this is basically for the equivalent lift that this traditional flap is giving us. This is the pitching moment that we would get if we were just trying to match the lift. And so you can see, we're still creating a larger pitching moment, a more negative pitching moment, but it's not nearly as bad as looking at it in terms of per degree deflection, because we didn't need this much deflection, right, in order to match the lift that the traditional flap was giving us. Okay, I think that's about it for this paper. Now the final, this is a copy of the journal paper, the preprint for the journal paper, and in the conference paper we actually had one more section, and I'll just draw a figure over here on the right and tell you what it was about. But we also looked at the parasitic drag. So we then included viscosity. We generated these airfoils in Xfoil and looked at the viscous results, or the drag ratio that would occur if we required both airfoils to have the same produce the same amount of lift at the same angle of attack. And so each required a different amount of deflection, but on the y-axis we put, let me just draw this plot here, and you can go back and look this up in that paper. We actually had to go back, in the original paper we had some errors in our data, and then we had to go back and correct that, but we published the corrected version of it. So if you go back and look at that paper, that conference paper, then it'll have a link to the published, the corrected version as well. And I can leave a link with this video as well to that paper. But anyway, on the x-axis, we have angle of attack, alpha, and then on the y-axis, we had delta for the traditional flap. Okay, and you can look at lift coefficient contours, and they basically look like this. So of course, as we increase our angle of attack, then our lift will increase, and these are increasing up here So let me draw that here. So our lift is increasing in that direction. And then of course, if you hold an angle of attack constant and increase your flap deflection, then your lift also increases. So these contours kind of look like this, okay? And then we went to the parabolic flap and we said, okay, so at this angle of attack, we choose an angle of attack, and then we say you have to produce, this much lift that falls on this contour here. And of course, the deflection of the parabolic flap was a little bit less, between 70 to 80% usually of the traditional flap. But then we ran both of those scenarios through Xfoil to compute the drag. So they're at the same angle of attack, same lift coefficient, and now we computed the drag, and we plotted the contours of drag on this figure. And at zero deflection, of course, they were both the same, and so we would get a line right through here. And then we got contours that looked something like this, where I'm just going to try to draw these contours. They looked roughly like this. Okay, where in these regions here, let me go to a different color. In these regions here, the drag ratio of drag was less than 1, meaning that the parabolic flap had lower drag than the traditional flap. And then in this other region, so those right there, then the drag ratio was greater than 1, meaning that the parabolic flap actually created more drag than the traditional flap. But what's interesting is that most airfoils operate in a region like this. So usually we don't operate at a high angle of attack and low flap deflection in order to drop our lift down. If we want to increase our lift, then we increase angle of attack, we increase delta F, and we're going to stay kind of in this region here. We usually do not try to, for at some lift coefficient, we could drop it by lowering our flap deflection to get down to a lower lift coefficient. But usually we're going to do a combination of flap deflection and angle of attack and follow a trajectory that goes more in this direction. So these contours, by the way, were maybe got down to about 80% in the extremes, and then closer in here, it's 95, 98, and then cross one, 98, 95, and then you can get down to lower numbers here. So anyway, there is a drag benefit once you include the parasitic effects, but they're confined to this region here. And if you go into this somewhat abnormal region, then the drag on the parabolic flap is actually worse than the traditional flap. But for most applications, it's most likely going to also have a decrease in parasitic drag. So there you go. This is a study of parabolic flaps, and of course you could assume a different geometry. We just assumed a parabolic flap, where this was a parabola, but you could repeat this study assuming a perfect circle. You could make it higher order. So instead of being a parabola, which is a second order equation here, we could have used a cubic or even a quartic or whatnot. We could have gone higher and higher in power and added boundary conditions that not only were the first and second derivatives, that not only is it continuous and the first derivative is continuous, but we could have made the higher order derivatives also continuous at the hinge point. Anyway, there's a lot of things you could do with this, but I think it's a very nice demonstration of how powerful thin airfoil theory is in allowing us to analyze different geometries like this and come to conclusions about what would be the most effective way to increase lift, or what's the most effective design of a flap.